Welcome to iSet Robotics into Gear on your mark. This is the fourth and last unit, and in this unit we're going to look at the design of attachments for your robot. In this learning unit we're going to look at the engineering design process, which is a way to solve engineering problems in a systematic way. And we will then apply the engineering design process to the design of robot attachments. With the help of an attachment, the robot can basically push, pull, lift or drop items. And we'll look at passive attachments and motorized attachments, where a passive attachment is constructed from the robotics kit without a motor, and the motorized attachment has an additional motor for the attachment that is used to move the attachment. Finally, in this session we will provide you with building instructions, a list of online building instructions for attachments, as well as recommendations of 2 good books that describe many attachments and contraptions in case you want to build according to instructions. So let's look at the engineering design process, and there are several ways to outline the engineering design process. The one that I have chosen from this class is from Engineering is Elementary. That's an engineering program for learners in grades 1 through 5 in elementary school out of the Boston Museum for Science. And what it has in common with all other engineering design processes is that it is a loop in which you work. So in the center you see the goal, and the steps to achieve the goal here are to ask, to imagine, to plan, to create, and then to improve. And you might have to reduce some of these steps depending on the success of your design. So, what are we going to ask? Questions to ask are: what is the problem? How have others approached it? What are your constraints? And constraints could be in terms of materials that you are allowed to use, but constraints would also be time that you have and the deadline by which your design needs to be accomplished. Next, there's imagine. So imagine some possible solutions for your task. Brainstorm ideas and pick the best one, or keep the 2 most promising ones in case that your best one doesn't actually work. And keep in mind that the brainstorm process is one where you're just gathering ideas and you're not judgmental on any of those ideas. So you just collect all the possible ideas that come to anybody's mind and you write them down, and you keep them for now, regardless of how crazy they appear, and then you evaluate them when you're done with brainstorming in the selection process. The planning step is one of first drawing a diagram. It's always good to have a visual representation of your plan. And you also need to make a list of materials you will need. You could plan the programming steps if it's for the robot. And then you're ready to create. In the creation process, keep in mind that the learners need to follow their plan, or you need to follow your plan to create something. Don't just create something that is totally unrelated to what you've planned in the previous step. And once you've accomplished the creation process, you need to test it. And then you can ask, well, you can improve it by asking yourself what works, what doesn't, what could work better, and then modify your design to make it better and test it out again. So depending on how many things work, you might have to go back to the ask, imagine, plan, or create step and redo the engineering design process from there. When you apply this process to a group of learners in robotics, it's important that you slow them down on the improve step. So they are not allowed to destroy their design until they've answered the questions of what works, what doesn't work. If they don't understand what is not working, it is unlikely that their next design will work any better than their previous design. They also need to take a look at minor fixes that might exist. Oftentimes there's something small that can be fixed and the main idea is still valid. So don't allow your learners to start again with the ask step until they've understood what was not working in their design and also until they've understood what did work well. Make sure they do plan what they want to do, and it helps them with their teamwork and then the decision of what to create. Okay, the engineering design process is something that we're going to practice by designing attachments to our robot. So far, our robot knows how to move, straight forward, back, turn, and it can collect inputs through its sensors from its environment. So why do we need attachments? Well, we need attachments because oftentimes the robot has to complete tasks that require it to push, pull, collect, deliver, lift, drop, or fetch items of various shapes and various weights. And the attachments are the tools that you add to the robot in order to perform these tasks. Now, in a competition setup or when the robot has to perform several different tasks that require different attachments, it is important that you design your attachments in such a way that they are easy to exchange. And when it comes to attachments, we can classify them into either passive or active attachments, where active attachments are the ones that require a motor to program the motion of the attachment. So a passive attachment is a mechanical structure that is added to the robot that in order to perform its task doesn't require the power of a motor. So a passive attachment typically allows the robot to push, pull, sweep, drop, or collect items. And in terms of real-world applications and machines, you can think of a bumper or a plow, a container, or a hook. Being a passive attachment doesn't necessarily mean that the attachment cannot move. It's just that it isn't a motor that makes the attachment move. Here on the bottom you see two different passive attachments. On the left there is an attachment that allows to carry a ball, and it actually has a pivot mechanism that tips the attachment to the front by the lever on its bottom as the attachment hits the wall of the bucket, and then the ball falls into the bucket. On the right hand side you just see a U-shaped plow or bumper attachment that could be used to collect items or push items to a certain location. Now in some cases you need a motorized attachment, so you need an additional motor to move the attachment where the rotations of the motor, then turn the attachment in some direction. And when we programmed motors previously to move the robot, we mainly used rotations to program the motors, because then the distance traveled didn't depend on the power of the motor or the speed of the robot. Here with motorized attachments, it's recommended that you program the motor using time as a mode instead of rotations. And that's because if you use rotations and for some reason the motor cannot complete the rotations that you programmed because the attachment gets stuck on an obstacle, the program won't proceed to the next programming block, but it will be stuck at that step because the number of rotations are never completed. If, however, you program your motor using the time mode, then the time that the motor is supposed to move will elapse regardless of whether the motor is able to perform the rotations you anticipated or not. Examples for motorized attachments are cases where you need to grab and hold an item, lift an item, hook up an item, or dump an item to perform a given task. So as I mentioned, the design of attachments is what we want you to do this week for given tasks, and we want you to apply the engineering design process for it. So when you're designing attachments, you can do it using instructions, or you can do it using more exploration. So there's kind of like a slider between 100% instruction or 100% exploration, and you need to determine for yourself where you want to place yourself and how you want your learners to attack the attachment design. So far, most of our lessons and assignments were more on the instructional level. We've done many assignments where it's just following instructions. Design a robot following building instructions. Program the robot following what you've learned in the programming instructions, and so forth. So you could look up instructions, and there are many building instructions, many excellent building instructions for attachments too, and use the instructional approach. Build this attachment and use it to solve a certain task. If you do that, it's a clear task, and the learners know what to do by now. It's fast and straightforward. However, the product they will design isn't really one for which they take credit and ownership. They've just followed instructions and done what they've been told, but there is a lack of ownership in what they've accomplished. Depending on which set of instructions they are using, the design might not be suitable for a given task. What is good with using an instructional approach is that it applies existing knowledge and expands knowledge, because if you have them test out various attachments from building instructions, they can then later on use that knowledge to pick and choose the one that they actually want to use for a given task. Now, when I teach a robotics class and it comes to this point in the lecture, I use more of the exploration approach, where I explicitly forbid the learners to use instructions for their attachments. I give them a task, and they need to solve that task, just being creative by brainstorming, designing, testing, improving. So using exploration fosters creativity, teamwork, and problem solving. However, it can be a little intimidating or fuzzy. Oftentimes you hear, but I don't know how to do this, ma'am. Can you help me? What do I need to do? So it's a task that learners are not used to in their typical school curriculum, and therefore it oftentimes is time consuming because it takes them a while to actually overcome the intimidation and try out something. Once you see the product, there is an ownership of the product because they're really proud of what they have accomplished, and they do feel that this is their personal accomplishment and that they are capable of designing. When you use exploration, you keep in mind it's time consuming. You need to give them the time to explore, to experiment, to take apart and improve. And it does need good troubleshooting skills to get to a reasonable outcome. You also risk of reinventing the wheel. Let's say you need an attachment, kind of like a forklift, and well, there is knowledge on how to design a forklift, so if you are not using it and you're just doing exploration, then you need to redesign a tool and you're reinventing the wheel. It does expand creativity among your learners, and it definitely helps them with self-efficacy and also self-confidence, because they get out of it saying, I can do this, I have the skills to design a robot attachment or to design a robot that accomplishes certain tasks. So wherever you want to place yourself on the attachment design, it is up to you, but we'd love to hear how it goes. Now back to instructions. There are a variety of excellent instructions available for all kind of different attachments and also robot designs. The EV3 Constructopedia focuses on sturdy structures and the design of sturdy structures with different types of robots. They all have 2 motorized wheels, but sometimes it's a wide robot, it's a narrow robot, it's a high robot, and so forth. Then EV3 Lessons has a lesson on passive attachments that you might want to look into. You can also go back to the Riley rover and look at the cargo loader attachment from the Riley rover. The Riley rover building instructions also have a grabber. You're welcome to build it and take a look at it. I personally don't like it that much because it breaks apart and you cannot move it manually while it's not connected to the motor. There are zillions of good YouTube videos about attachments in FLL competitions, so you might want to take a look at one of them or Google for more of them on YouTube. And there is the modular test vehicle, where they provide you with some ideas on how to design your robot out of various modules that you can add and remove from the robot to obtain different capabilities. There also are 2 excellent books. The LEGO Mindstorms EV3 Idea Book has zillions of contraptions, simple machines and attachments and gear mechanisms for the EV3 robot. And then there's the LEGO Mindstorms EV3 Discovery Book, and it is definitely worthwhile looking into both of them if you have them available. And then, as always, in case of questions, please don't hesitate to contact us.